Hi, welcome back. In this video, we're going to be working through the solutions to the vector worksheet. So, when we talked about vectors inside our pod or inside our Nearpod in our lesson, we talked about when we graphically add vectors, we want to add them always head to tail. And we found out that as long as they were parallel or epiparallel or perpendicular, that wasn't too bad. But once we started getting them when they weren't that, when there's some other angle other than those, if they're 0, 180, or 90, things got a little bit more complicated and you had to draw them. And so if I wanted to add these two vectors, if I wanted to add this vector here and this vector here, what I'd have to do is I'd have to redraw them. And so I'd have the one going up like this, and this is going to be a bad combination, but you kind of get the idea. And then this one down here, I would add head to tail, so this one would come down here like this. And so my resultant, okay, and I can't guarantee that this is going to be a right angle. I don't know that for sure, so I can't necessarily put that in. And so, in fact, in this case, it definitely won't be, though it kind of looks like it's close to it. But my resultant did this. And so, in order to find that, we would have to then draw all of these to scale and measure it out, Well, the next thing we talked about was the analytical adding of vectors. And that's by using our right triangle powers to create right triangles, to break apart a vector into perpendicular pieces, and then put it back together in ways where we know that it's easy, especially when they're parallel, epiparallel, and perpendicular. In this worksheet, that's what we're going to be working on. Okay, and so the first step is you have to be able to break apart vectors. Okay, so first and foremost, any vector that's acting at an angle, you are definitely going to want to always break apart. That's just a great rule of thumb. So if I just take a look at this one right here, it says you walk 50 meters at an angle of 25 degrees north of east. So this is 50 meters long, and this angle is 25 degrees north of east. And so it asks how far east and how far north have you traveled. What I'm asking you here is, can you break apart this vector into a piece that goes horizontal, in this case is east, and a piece that goes vertical, in this case north. And this, because it's horizontal, because it's vertical, this is going to be a 90-degree angle. And so essentially what you've done is you've created a right triangle. Now this is the one part of trig that you are going to have to know. You're going to have to be able to find out these sides. So I know, and this is just a quick review, and I'm just going to do this over here. When I have a triangle that looks like this, and this is my right angle, this side right here is my hypotenuse. The side that is across on the right angle, it's the biggest side. Okay? This side down here, hang on, let me put this in. This is the angle here, if this is theta. This side down here in the bottom, this is my adjacent side. And the side across is going to be my opposite side. Now, if you remember, and I'll put this in, Sohcahtoa, this is what we're going to be using. Sohcahtoa and Pythag are the two theses we're going to be using in all of this. If you don't remember it, though, that's okay, because in your reference tables, it gives you all of this. So what we're looking for is, we want to find out how far east. Well, that means I need to find my adjacent side. I need to find this. Okay? Using, in this case, ka, I'm going to say that my adjacent side, actually the cosine of 25 degrees, is equal to my adjacent side, which is what I'm looking for, divided by my hypotenuse. So in essence, we've gone back and we've gone guess, because we know our hypotenuse is 50, we know our theta is 25, and our unknown is the adjacent side. So when I cross multiply this, so that's going to get rid of the hypotenuse and put 50 here, 50 meters, that gives me an adjacent side of 45.3. Now I'm rounding, and I'm going to round everything. Basically, my rule of thumb is I always want to round to one more decimal place than where I think I'm going to be at the very, very end. Okay, just because it's easy. I don't like to write out all the digits because that's kind of a waste of time. Okay, and I don't want to round too harshly, so I always try and go one more decimal place than where I'm going to be at the end, kind of thing. So this is 45.3 meters. If I'm looking for this, this is my opposite side. And so for that one, I'm going to use sine. So the sine of my angle is the opposite side over the hypotenuse. So the sine of 25 degrees is my opposite side over my 50 meters. And so now my opposite side, cross multiplying that, gives me 21.1 meters. So what I've essentially done is I've broken up that 50 into two pieces. If I were to walk a displacement of 50 meters at 25 degrees north of east, it's the exact same thing as if I walked 45.3 meters east and then turned and walked 21.1 meters north. I would get to the exact same spot. Okay, so that's kind of what we're going with this. In the process, when I break it up, I kill off the 50. So now I'm done with that. Okay, now let's take a look at the next one. Exact same process here. You turn and walk at 40 meters at an angle of 50 degrees south of east. How far south and how far east have you moved during this walk? So if I go here, what I'm going to do is I'm just going to make another right triangle. Here is my adjacent side. Oops, I forgot to label stuff. My fault. Let me change this, put this right in here. This is 40 meters, and this is 50 degrees. And then my opposite side is coming down. This is my opposite. It's right there. Once again, here is my right triangle. And so once again, I'm going to use sine and cosine to find these. The adjacent side, I'm going to use cosine of theta is the adjacent side over the hypotenuse. And so the cosine of 50 degrees is equal to the adjacent side divided by the 40 meters, cross multiply, and my adjacent side now becomes 25.7 meters. My opposite side, I'll give that green, I'm going to use sine for this. Sine of theta is the opposite side over the hypotenuse. So the sine of 50 degrees is the opposite side, what I'm looking for, over the 40 meters. Cross multiply that, my opposite side becomes 30.6 meters. Okay, so now what I've done is I've essentially broken up the 40 meters. Okay, so again, if I were to go 40 meters at 50 degrees south of east, that would be the exact same thing as if I walked 25.7 meters east and then turn and walk 30.6 meters south, I would end up in the exact same spot. Okay, so why? Why do we do all this? The whole reason to do this is because of number 3. Add the previous displacements to determine your total displacement. So remember, if we want to find total displacement before, we had to draw a picture. I must have gotten rid of it. We had to draw a picture that looked like this, and then like this, and then a resultant went like this, and sometimes it was good and sometimes it wasn't, but I can't believe I got rid of that. Okay, whatever. So, but we had to draw that to scale, okay? If we do it this way, what I've done now is instead of adding two vectors, right here, I'm adding two vectors together. And you're thinking, okay, great. Now, though, when I break up my 50 and I break up my 40, what I've essentially done is now I've gone to 4 vectors. Now, most people are like, why? That's insane. Why would you want to go from adding 2 vectors now adding 4? Why would you want to make your life more complicated? And the reason for that is because if I look at my orange arrows, again, I'm going to take this orange arrow that's right here, my adjacent side of the first one, and I'm going to draw that like this. I know that that's 45.3 meters. In my first displacement, I went 45.3 meters east. If I look at the other orange arrow, this one went 25.7 meters east. Now, looking at these 45.3 and 25.7, these vectors are parallel. I can add parallel vectors really, really easy. All I have to do is add them. So I just bring this here. Oops, just a quick little redraw. Let me just try and do it again. I'm doing this freehand, so that's why it looks like. Ugh. So that's going to give me 71 meters. And so in my displacements, when I went 50 meters at 25 degrees north of east, and then I turned and went 40 meters at 50 degrees south of east, I essentially walked 71 total meters east. Now, if I look at the green, and I'll draw this down here, I have 21.1 going up. 21.1 meters. and I have 30.6 going down. Now the rules still apply. I still have to add them head to tail. So now I'm going to put this in. My 30.6 is going to start right here and move on down like this. This is my 30.6 meters. And when I look at these are apiparallel. And so now when I put these two together, I end up with one vector that is going to be 9.5, and this is really a scale, let me try that again, 9.5 meters long. These are these two added together. So now I've gone from, let's rehash, I've gone from adding two vectors right here that were not parallel, not perpendicular, not apiparallel, tough to add, to adding four vectors, which is silly, but now wait. Oh, out of those four vectors, two of them are parallel, two of them are apiparallel, and once I put those together, I'm now left with two vectors. Now I will circle this in blue. I have one vector that goes east, one vector that goes south. And so if I take this one, and I'm going to actually pick this one up, and I'm going to actually, I'm going to copy it. Let's do that. Copy. And then I'm going to paste. So here's my vector. I'm going to take this and I'm going to attach this head to tail right there. Now I have two vectors that are perpendicular to each other. Let me zoom in. These are perpendicular to each other. Maybe. There she goes. And so now my resultant, tail of first, oops, that's going to be ugly. Tail of the first ahead of the last. This is what I'm looking for, right there. I can now find out how big that is. This is a right triangle. I can use Pythagorean Theorem. A squared plus B squared equals C squared in order to figure out how big that is. So in this case, 71 meters, don't forget to square it, plus 9.5 meters, don't forget to square it, is equal to C squared. And when I find that, C is going to end up equaling 71.6 meters. Or if I wanted to round it to the nearest ones, 72 meters. Okay, I'm going to leave it as that for right now. The other thing that I have to know about vectors is I have to know the direction, which means I have to find the angle. I'm going to find this angle right here. This is my question mark angle. I need to know what direction it's headed. Well, the way I can do that is now I know all three sides. So I could use sine, I could use cosine, I could use tangent. I personally always use tangent because I know my adjacent side, I know my opposite side, and so I'm going to do it that way. So I'm going to use tangent here. So my tangent of my angle, I'll put this in black, tangent of theta is my opposite over my adjacent. So that's going to equal 9.5 divided by 71. And if I go 9.5 times divided by 71, hang on one second, let me just crunch that through. 9.5 divided by 71, I get a really small decimal. That's 0.1338 is my decimal. That's equal to the tangent of theta. So what I have to do is I have to take the inverse tangent of both sides. So theta will equal tan to the negative 1 of 0.1338. This I anticipate some of us may have some issues with. Please, if you do, come see me. Okay, it's a calculator work, and once I teach it to you, really simple. But initially it gets kind of like, whoa. So if I take the inverse tangent of my 0.1338, I get 7.6 degrees as my angle. And so I just have to label this 7.6 degrees. And so my answer when my total displacement is 71.6 meters at 7.6 degrees south of east. I don't have to know the south of east. As long as you label your diagram, that's fine. You don't actually have to write it. You just have to have this part right here and this part right here labeled on your diagram, and that's good enough. Okay, let's take a look at the next one. Here, I've got three forces all acting upwards on this couch. I want to find out the total or net force, which means I have to do the vector sum of all of these forces. Now, without doing it, or without doing it analytically, what you'd have to do is you'd have to draw this one. And so this one would go 50, and then you'd have to on the 40. Oops, let me do that just a little bit better angle. So I'd have to do 50 here, and then I'd have to tack on the 40, which goes straight up. We draw head to tail, so there's the 40. And then I'd have to draw the 30, I'll put that in green, to be like this. Oops, that's going to come over just a touch more. To be like this. And so there's my 30. And so my resultant is going to look something like that. Now again, since they're not parallel, they're not equiparallel, they're not perpendicular, this is challenging to do and challenging to get a right answer. So we're going to do it analytically, which means I have to break all of these up into pieces. So now the 50, I'm going to break that one up into a piece that goes vertical and a piece that goes horizontal. And the way I do that is by using sine and cosine. So this side, I'm going to use the cosine of theta is equal to the adjacent over the hypotenuse. You're like, well, wait, what was the angle? Well, it tells you right here it's 20 degrees. So I'm going to put that in right here, 20 degrees, 20 degrees. And same thing here. This is also at 20 degrees. And I'll put that one in as well. Okay, so on these two, I'm going to use the cosine of theta is the adjacent side over the hypotenuse. So this one right here, cosine of 20 degrees equals the adjacent over 50 newtons. And so when I do that, I find that I get 47 meters is up. If I do this one over here, I find that I get 28.2 newtons up. Not meters. This should be meters. Sorry, that's my fault. That should be newtons because we're in a force right now. 28.2. Let me erase that. 47 newtons, 28.2 newtons. Okay. If I do the green ones, because they're opposite the angle, I'm going to use sine. So for this one, I'm going to use the sine of theta is equal to the opposite over the hypotenuse. Here, sine of theta, opposite over the hypotenuse. And so when I do that one, I find that this one up top is 17.1 newtons. This other one up top is 10.3 newtons. Okay. And then you're like, well, wait, what about the 40 one? How can we do anything with the 40? The 40 is already straight up and down. I don't have to break that up. I only have to break up vectors that are acting at angles. Those are that's got the rule. If they're straight up, if they're already vertical, they're already horizontal, I'm not going to mess with them because life is easy. Okay? So now what I've done here, remember, when I break up the vector, it's dead. So I've killed off this 40, or this 50. This 50 is dead. I've killed off this 30. It's dead. I now, instead of adding 3 vectors, I'm now adding 5. And again, that seems silly, but remember, I'm going to draw this over here. I've got 47 up. I've got 40 up. And now I've got 28.2 up. Since they're all parallel, I can just add them all up and get a whopping 115.2 newtons. If I look here, and I'll circle these in my orange pencil. Now I'll go with the red color. This one and this one, those two vectors are equiparallel. So I have 17.1, I'll slide this over, 17.1 pulling to the left, and then I have 10.3 going to the right. Those are equiparallel, so I'm going to subtract them, which is going to give me now 1 going to the right, and I'm just going to put it down here, 1 going to the right of 6.8 newtons. And I got that by taking 17.1 minus the 10.3. Okay? So now if I redraw this one last time, I have one big tall one, which is a 115.2. I have a little teeny tiny green one of 6.8 going to newtons going to the right, left. And now my resultant is right here. And you're like, well, how do I find that? Remember, this is a right triangle, so I can use Pythag. So 115, I'll put this down. I'll keep this in purple, sorry. C squared equals A squared plus B squared. So C squared is equal to 6.8 squared plus 115.2 squared. So C squared kicks out to be 115.4 newtons. I also need to find the angle. I'll put that in black right here. So again, I use tangent on this one. So tangent of my angle is the opposite over the adjacent. So tangent of theta is 6.8 over 115.2. I said the wrong one. So my angle kicks out to be about 3.4 degrees. Now, some people are saying, well, wait, how did you know to do that one? How come you didn't do this one up here? And I'll put this in rainbow here. How come you didn't do this one right here? I could have. And as long as I labeled it, I would be fine. Okay? And so that one, when I did it, that would have given me an angle of about 86.6 degrees. And that's fine as long as I've labeled it. I'm good. The only angle you can't just say, oh, it's at 90 degrees. That's not going to work. Okay, so that's the end of the vector. Again, this one gets a little bit complicated. So again, try some of the should-dos on this and come see me if you have help. All right, have a great day.